great. Thanks for coming as well, and thanks to everyone for joining virtually on the meetup today. Jamie and the team have got some exciting stuff that we've been working on at Invivo. So, we like to embrace the latest technologies. We've got a big plan in terms of the technologies that we're developing into and the product that we're developing for our clients and for our future clients. So, we just want to share what we're doing and get feedback from you guys on what you're doing. And this hopefully will be one of sort of many meetups that we do now. As I said, from our perspective, we want to become part of the Manchester community from a kind of technology and dev perspective, and just become part of this. It's exciting for us to be here, and really looking forward to this one as our first meetup, and hopefully many more. So looking forward to this, Jamie. So thanks very much.
Thank you. So the kind of idea is we'll do these about once a month, try and do it around the same time probably, but obviously things may change as we go along. Generally, it's going to be all roughly event driven, but it's going to be flexible in regards to if people want to talk about something that's tangentially related, like microservices or whatever else really. We're open, we want people to volunteer, so if there's anything you want to talk about, please come to us. Are you okay with I was hoping to share, that's fine. Similarly, we're going to have some speakers coming in the next, probably the next event when we do, or, we're going to have speakers from Microsoft attending and speakers from Confluence, and we're going to be reaching out to some other companies to see if we can get speakers from them. But yeah, we've already got some from Confluent and Microsoft that have agreed to come and speak for us, so either in person or remotely. So I think we can get some exciting talks done, and hopefully we can all learn a little bit on the way. And I think we've already mentioned some of the social aspects, and learning from each other is what we're kind of a lot of us are interested in. So hopefully it's an opportunity for us all to share. So even if you're new at the event sourcing, event driven, whatever architectures, if you're new at that stuff but you want to talk about how you found it, how you've learned, what some of the difficulties are, things you've overcome, please come and do a talk, because we'd love to hear how everyone's finding it. So on that note, I will start us off with our first talk, which is mine, which is let me share my slides, and it's basically event sourcing. So what is event sourcing and why do people use it? So I'll share my screen. Can everyone see that okay? Yes, looks good. Okay, perfect. So what is event sourcing? So obviously this is an event-driven architecture meetup. Event sourcing is one of the more popular event-driven patterns, and it's one that I've got more experience with, so I thought it's a good one to start us off and talk about. But to first start, I think it's good to actually move to the next slide. There we go. Talk about history. So yeah, surprisingly, event sourcing has actually been around for over 4,000 years. Ancient Babylonian empires used tablets to record events as they occurred, which were financial events and things like crop trades and stuff. Greg Young talked about this in his video. I'll mention Greg probably a lot in this talk, because he's kind of one of the pioneers of event sourcing as an architecture and as a name. And a lot of this stuff is things I've learned from him and learned from watching him attending his talks, and kind of tried to build on that. So it's something that's been around for a long time, but it's something that's still used heavily today. A lot of financial, insurance, healthcare, law, things like industries like that use event sourcing, because industries where it's very, very important that we know exactly what happened and why it happened, they tend to heavily use event sourcing as architecture. Databases run event sourcing. I'm going to go over what event sourcing is in a minute, and I'll explain why, but basically every database you use will be probably using an event sourcing model under the hood. Similarly, version control systems use event sourcing. Git, that probably most of us have used, uses event sourcing under the hood. And through this, basically every piece of software you use almost certainly is using event sourcing either directly or indirectly. So what is it? So event sourcing is actually really simple, and this is why it's been around for so long. It's just storing our data as an ordered list of append-only, immutable facts or events. So we don't store mutable state like you traditionally would have done. We don't update an entity or event when something changes or something occurs. What we store is a new event. So, for example, if a customer is updated, rather than updating the customer entry in the database, you would instead issue a new event that is the customer was updated. But then the difference is we keep those events forever, so we don't ever throw them away. So here's an example of a log, an immutable append-only log, where you go from 0, 1, 2, 3. And this gives you some nice features straight out of it, because, for example, you can see the order events happened in. Even without having to agree on a centralized clock or time system, you can at least agree what order things happened in. And here's an example where that might be important, and this comes straight from NVivo, one of the things we're doing. You might create a template for an SMS, then make a send SMS request, and then you want to get an SMS send result. So there's three things, and actually that third is a bad example of an event, because that should be SMS send that has a result object on it. But the point is there are three different events. Imagine the last one says SMS sent, and they are something that's happened. We're not modifying the state of an SMS object in a database. We're adding a new event every time something different happens. And that can be the same one. If you might retry that SMS send, you might retry and send that SMS send requested multiple times, and you end up with multiple SMS sent messages or SMS failed to send messages or whatever you decide you have in your recording. So some of the technologies that use event sourcing or that let you build event sourcing architectures are Event Store, which is by Greg Young, who I mentioned earlier, Kafka, AWS Kinesis, Azure Event Hub. There's many more, but these are some really popular technologies that are being leveraged heavily. We use Kafka at NVivo, but we've also used Event Hub, and Kinesis is very similar, and Event Store is something I've used in other companies that's also very powerful. So here's another example. You have a user in your system, whatever system it is, they want to update their email address. In a traditional database, we would find the user in the database, we would update the email column with a new value. Easily done. In an event source system, we issue that new event with the new email address. So the event might be user updated, it might be user email updated, user configuration saved. The event can be however your system decides best to model it. But the point is that event has now occurred. And that means that when we go in the traditional database, we would have lost access to that old email address because we've overwritten it. We've destroyed that data. We could have had some kind of audit table if we'd thought ahead. We could have said, okay, let's build an audit table for these changes. But if we better hope we're testing that audit table, because if not, and what often happens is you have this audit table that the system isn't actually using. So no one actually is checking the audit table is correct. Maybe there are some tests, but if the front end isn't driven from it, so there could be bugs in there that you don't even know about. In an event source system, however, we're storing that as just another event on our event log. We're adding it as a new event on the event log. But the whole point is our database is the whole stream of events. So we have the current email because that's the latest update. We have the previous email because that was a previous update. But we're not getting rid of any other changes. We have all the changes that user has ever made to any of their data, and we're not getting rid of anything in between because we have the whole event log. We know our event store audits are there because they're the whole database. And we know they're correct because that is exactly what drives our screens. That's what drives our application in its whole. We know it has the same structure. We know it has the same, it's the same database, and it's not segmented in any way. It's not archived away somewhere else, so it's accessible in the exact same way. If the user comes to us 6 months later and says, why did you send an email to this email address? This isn't my email address. In a traditional database, at best, you might have a modified date that tells you something changed. If you're really lucky, there might be a table, there might be a modified field date that tells you that field was changed at a certain date. But unless you had predicted that you needed to audit these changes, you won't be able to see what the old email address was and see what it changed to. In an event source system, you automatically have that full history. So not only can you see what it looked like at that point in time, you can actually go back. You can roll your data back to what your entire system looked like at that point in time, because sometimes it isn't as trivial as an email address. Sometimes it's some complex behavior that is actually the result of 3 or 4 different sets of data all intertwining and causing some specific output. Well, we've now got version control for our data based on this. Because we're storing every piece of data and every delta and every change, that means we can roll back our data to exactly what it looked like at that point in time. We've all seen source control, so we all know we can do the same thing with our code. So by rolling your code back to what it looked like at that point in time, by rolling your data back to what it looked like at that point in time, you can then replay the events and have exactly the same output in a deterministic manner, because well, that's what the data looked like, that's what the code looked like, If you have infrastructure, immutable infrastructure, and infrastructure as code, for example, you can even build your infrastructure so that it's as it like at that point in time. And then you really know that everything that's at least within your control should be exactly the same. As long as something underlying hasn't changed, like a network, like it was a bug in Azure or something they've since fixed, you can exactly reproduce that any issues. And that becomes really powerful. So how do I query the current state of the user though? So when we need to know the current state of the user, because we have this long list, we can iterate over all the events to calculate it. So for email address, that's quite straightforward. We iterate over all of them, and whichever the last value we find for email is, that's the email address. For if you're building, I mean, another common example of this, we talk about in financial systems, they use event sourcing to track your bank balance, for example. That's your bank balance is an event source thing. There is no row in the table somewhere that says your current bank balance, or at least if there is, that isn't the source of truth. The source of truth is every bank transaction that's ever gone through. And this is a common example because it's really obvious to people, but to calculate your current balance, they go through all the credits and all the debits to your account that's ever happened and calculate it. That's great. That means you can say exactly where it came from. But what you can't do is do it quickly because someone could have so many transactions to build through. So yeah, as you recognize, this can be slow. If you have billions of data points, you need to iterate over, and this is happening every API call. That's not feasible within a reasonable amount of time. This is where CQRS comes in, and you may have heard of this often talked about with event sourcing as a pattern. But CQRS is basically command and query responsibility segregation. So simply put, this is about taking your commands, which are updates really, and queries, which are reads, so writes and reads, and using separate models. So we make sure that our reads are different to our writes. We allow ourselves to optimize those models different. So we've already got event streams. We've already said we're using event streams for our event sourcing architecture. Event streams are very fast to write to. So we talked before here, it's just a log. It's just a log of things that happened, events. That can be saved as a text file on a drive. That's nothing clever about that. There's nothing special. Obviously, tools like Kafka and Event Store and things like that and Kinesis, they do a lot around that to make them easier to work with. But at the end of the day, that is your event log. That is your database. It's a list of, it can be a flat file, just lines on it. So the point is, when you get to the point of writing to that, when we're writing to that, that's it, that's trivial. That's writing to a file. That's very fast. So we can write to it very easily. We don't have to worry about the writes. But the reads are slow, as we've said. Reads are problematic. So how do we deal with reads? Well, what we can do is, as the writes are happening, we can be already pushing that data into read optimized views. So this is where the CQRS helps us, because then when data is requested, rather than having to iterate over the whole event log and calculate what the state is for that query, we instead just go to our pre-built cache, you could call it. It's an optimized read view, and we fetch that data. This derived view is transient. That's why it's called, that's why it's derived. It's all coming back from the event log. The event log is the source of truth, but the derived view is a much more optimal way of querying it. So even people using traditional SQL databases end up usually sharing one model of the data of the view that they have to use for both reads and writes, which means they can end up optimal. So you'll often see systems having to optimize themselves either for the reads or for the writes, and usually not for both. Sometimes they do, and if they do, that's CQRS. And that's exactly what you end up doing with event sourcing. It just kind of forces you to do that because the reads are so slow otherwise. But the advantage you get from that is that you can throw away those derived read views. You can store it in whatever optimized structure you want. You can denormalize it. You can do what you want to that read data. You can duplicate it. You can anything you want. Enrich it with data from the sources. That's all great, because as long as the source of that data is your event log, you can throw the derived data away and rebuild it. That is really powerful. And to put it clearly, because this is a really important point of the CQRS part, state is a projection of our event stream. It can be stored in SQL, Mongo, Neo4j. You can store that state wherever you want, and that's what you should do. If you're doing lots of complex queries, you'll want to use a relational database because they're good at doing joins and aggregations and all those kind of things. If you're doing simple lookups, you want to use probably some NoSQL store that's just really fast at looking at given keys. You've got those options. And the digital source of truth is never changing. I only say digital because Greg Young makes a good point that the real source of truth is the real world. If you're recording the number of widgets in a warehouse, your event log says one thing and the warehouse says something else, the warehouse is right, your event log isn't right. But other than that, other than the real world, being the real source, the digital source of truth is your event log. This means whatever data we need is still always in that event topic, but we still have the advantage of the SQL optimized view or whatever technology you want to use that's ready for us to query. And it's worth mentioning that event sourcing without CQRS wouldn't really work. You could probably do it if you had very small sets of data and it'd be fine. But in reality, no one's using event sourcing without CQRS. But the inverse isn't necessarily true. Lots of people are doing CQRS who aren't using event sourcing because it's just about separating those views. And I think it'd be good at some point. We will probably do a full talk on CQRS because you can go into lots of detail about the different strategies and optimizations when you're not doing event sourcing, but our event-driven architectures. But the core point there is that they're not necessarily coupled. Other than if you're doing event sourcing, you probably will almost certainly want to do the CQRS, but not the other way around. So with our data model we've talked about with event sourcing, if you think about the CRUD approach, create, read, update, delete, you've gone from CRUD to CR. You have a create, you have a read, you can't update and you can't delete. So event sourcing is the only structural model that doesn't lose data, unless your structural model is basically an implementation of event sourcing. It's basically the same thing as event sourcing. So a good question to ask yourself is, do you perform updates or deletions on your data in your day-to-day jobs? And if you do, how can you be sure, 100% sure, on what data you're going to need in a year's time or even 5 years' time? How do you decide what data is going to be destroyed? Because when you're overwriting data, updating data, deleting data, you're destroying that data. Unless the CEO or the business has signed off on it, how do you know that's not data that's going to be valuable down the line? And even if they have signed off on it, how do they know that what data is going to be valuable in a year, 5 years' time? And in reality, most companies are destroying vast amounts of useful data every day that they could well need in the future, and that they could use to give themselves that competitive edge, but that they're not able to utilize today because they don't have the staffing or they just haven't thought of it yet, and they don't have the opportunity to kind of grow into it in future because by that point the data's gone. And that's why you see these things where you're introducing machine learning, but then you need to spend 6 months building a big enough data set to actually start training it because you weren't recording that data historically, you were overwriting it. So here's an example of exactly that. Let's say in 18 months, someone comes along and asks your development team for some data analytics going back several years. They say, well, this should be easy. It's data you've definitely ingested. The customers have been sending us this data. So can you guarantee you've got all that data that customers have ever sent you? Can you guarantee it's not been modified since it was created? Is it just, and the really critical point is it just as easy to access? Because some people will say, yes, you can get that data. It's in our backups. We take nightly backups. So you can go back to the backups and get all the data you need. But if I'm building a team and trying to deliver some value, and I'm going to have to spend weeks or months building scripts to extract the data from the backups, that suddenly makes the value proposition for what I'm building massively different. And actually, this is, again, one of the things that Confluent and Jay Krebs and the guys who came from LinkedIn who built Kafka were trying to solve was easy access to data. I mean, theirs was more across the organization, but it's the same kind of idea that if data is not easy to access, suddenly you start getting these hurdles because you can't just go and access the backups. You have to go to an IT team and get them to open those backups up to you, get you access to them. You need to then figure out how to format them in the right format. You need to go and talk to the team who built them in the first place and figure out how they encoded them, what technologies they use, what mechanisms they use for serialization. All these things suddenly become really difficult. And before you know it, something that could have and should have been quite a simple win, an easy win for the business, becomes basically not worth the effort because it's going to take you 6 months to even get the data available to do the job you want to do. So what are some of the advantages of event sourcing as an architecture, of storing these events iteratively? Well, data structure changes are fine because you have to evolve your model that you're pushing into your message, through Kafka or whatever that you're storing as your logs. But your model in your database, your model in your front end, your model anywhere else is fine to change because there's no migration to make. You just throw it away, throw that database away, rederive it from the source data, which hasn't changed. So because you know they have the source data, there are some disadvantages of this, which I'll talk about in a minute. Because you know you have that source data, you know you can go back to it and rederive the data. So when you figure out we need an extra field in our DTO that we're sending from the API to the front end, that's fine. Just add that field rederive, and if you need to rederive some intermediary state store that you were using like SQL, throw it away, change how your derivation works, and rederive it. We have another advantage, we have a full and provably correct audit history, for our system. And that's the provably correct is the key part, because you can write anything you want to go to an audit table, but unless you're actually actively testing that, and the best tester is users using it, unless you're actively testing it, you don't know that the right data is being stored, the right data is retrievable. The difference with an event-driven system is those logs, that your audit log, is literally what drives your system. That is your system. So if you make a mistake and you're not recording the right thing, well, the users are going to tell you about it because the screen's going to be wrong. The results you're giving is going to be wrong. So you get this audit log, provably correct and basically for free, because the tests you're writing to test the system behavior are testing your audit log. There are some caveats around that. When message schemas evolve, you need to make sure you don't evolve your schema in such a way that old messages won't be processed anymore. And again, I'll talk about that in a second, but at its core, it gives you the opportunity to solve that problem. We can also, and this is what I mentioned before, but we can also see what the system looked like at any point in time, historically. And a really key part that I like a lot about this is you can see what it would have looked like at any point in time. It becomes a really powerful what-if machine. So you can say, okay, we made these predictions. Let's say you're making a stock trading application, right? And your application makes stock predictions. And it says, buy this stock, sell this stock. And it's not been performing great, right? It's been not beating the market. It's been, no better than really just following an index, investing in an index fund. But then you have this genius idea of what you could have done. And you think it would have been right, but you're not sure, but you think that would have improved performance. Well, you've been tracking, obviously the stock history is all online, so you could just pull it from that. But let's say some more proprietary data than that you've got. You've got some data that's really proprietary that you wouldn't be able to just get online. What you can do is, if you've been storing that in a database, you won't have the history necessarily. But if you've been storing it in an event sourcing system, an event sourced architecture, an event sourced database, you'll have the full history of everything you did. So you can go back to what your data looked like at that point in time, but run that data with a new code base. So a newer version of your code with some new feature, for example, taking into account some more data. And then you replay those events and say, had I had this information, I would have made these decisions, and that would have had this outcome. So it becomes a little bit like a what-if machine. And you can do that with your customers as well. You can say to your customers, if you'd paid extra for this module, we could have made these decisions for you instead. This module would have let you do X, Y, and Z, which would have been more beneficial because that would have had this outcome. So it's really key that you can go back and you can see what the system would have looked like had you done something different at the time. And again, if you're overwriting the data, you can't know, even if you have an audit table, it's not going to be trivial to replay your audit table into the original table to see what the system would have performed, and then replay all the events as they happen back into your original table. That's going to take some work to get that working. And it relies on your audit table being perfect. The event source system does that, gives you that again for free. Another advantage, accessing old data is just as easy as accessing the latest data. So we again mentioned this before, but this is great for teams coming in to add data analytics or machine learning or just a new feature where they want to come in and they don't want to have to worry about how do I work with you to get this working. They just say, okay, you're storing your data in Kafka, you're storing your data in Kinesis. It's an event log. I know how to work with that. I can just read from your log. And because of how logs work, if they're reading from the event log would impact you because the disk reads that fast enough, it's very easy to split a log. You just copy it. It's a immutable append-only log, so you can just copy it. And this is what databases do. Databases are backed by append-only logs. That's your transaction log. That's exactly what's happening in the database. And when you sync, for example, SQL, all it does is ships that transaction log off to another system and replays it to rebuild the database in the same way. And it's the same thing when you're wanting to get another team to work on the same data as you without stepping on your toes, interfering with you. They can just take a copy of your data, a real-time copy of your data, and work from that. And there's no worries about scalability or, well, we can't send you that data because it's going to impact our systems. We've had that with suppliers, Rich, haven't we? Where they can't send us data because, I was saying we've had that with suppliers where they can't send us their data because it's going to impact their live systems too much. Big names that you'll probably be surprised at, but they can't send us their live data because it would slow our system down too much because we can't read into a file and send it to you and then also read for our daily processes. In an event sourcing system, you can just copy it because it's just a transaction log. And that's, sorry, I've already said the next part. Immutable data, very easy to scale. You just do it. Caches that never expire are very common, because if someone's going to look at a very specific event in your API, that event will never change. So you can actually just have a cache that never expires. So if you're using Cloudflare or whatever, you just have a permanent cache, never expires, and all requests can just return the same result. Perfect. Smoke testing, easy. I mean, this is something that's, might take a little bit of work to set up, but once it's done, it's very powerful. You can rerun every command. When you're doing a new deployment, you can rerun every command the system has ever had. And you can compare the log results, the output logs, compared to the input logs, and see, well, what's the difference? Is there any difference? Because if you've not expected behavior to change, but the logs you output are different to the logs you will output from the last version, you know something's changed. And this is kind of like a Jest snapshot, but if any of you use that for testing your front ends, but on steroids, this is what the system got in, this is what the system got give out, and comparing to the others. It's like A/B testing or black box testing, but you get it for free because you can just easily push your event logs through. Every time a new message gets produced for your application, a new event occurs, that's a bit more test data you can use to test that when you're doing your next deployment. And as I talked about before, predictable I/O. Append only means sequential data writes, and because of this, writes are very, very, very fast. Kafka, again using that as an example because we know it, they don't try and optimize writes anyway. They don't like cache stuff in memory before they write it to disk. They don't worry about any of that. They let the operating system handle all that, and they just say write. Because these are append only writes, there's no random access. They are lightning fast because of that. They can do crazy amounts of data to disk, and that basically becomes their bottleneck because the system is so simple. It's just your disk speed, and even with slow disks, sequential writes tend to be very fast. And same with reads. Reads are sequential reads because you generally can't and won't jump to a specific event in your event log. You generally start at the beginning or start at some point where you left off last time, and you read forward the rest of the events. So that means there's no worry about, well, how do I have a really fast SSD that has random access? No, that's not a problem. You can have disks that are just good at going through sequential reads are fine. That's all you need. And this means that slow disks or cheap disks still work very well, but also, even if you've got fast disks, it lets your OS do what it does best and optimize that for you. And that keeps Kafka simpler. It keeps other, event sourcing systems simpler because they don't have to optimize any of that. And it means your lives are easier because you don't have to worry about what if something's in memory and then my node crashes. How does the system handle recovery from that position? Because the way it handles that is it lets the operating system handle that. It tells the operating system, write this to disk, and the operating system will write to disk. Another one, and this kind of talks again, is something we mentioned earlier, bugs are easier to resolve, especially when there are knock-on effects that have put the system into an unusual state. This is something I'm sure lots of us have encountered before. A user's hit a bug, but they've kept working. They've managed to work around the bug in some way, but the system's now in a weird state that no one really predicted would ever happen. Well, there's two massive advantages to event sourcing here. One, we can see exactly what the user did because every action is recorded. LinkedIn, for example, who I said pioneered Kafka, they record every single mouse movement you make on their UI while you're on LinkedIn. So they know that's how much data they're storing as well. Every mouse movement is being recorded. So they can look at exactly what you did to cause that bug. They know every action you stored. Not only can we see exactly what they did, but as we talked about before, we can roll the system back to exactly what the data looked like at that point in time that bug occurred. So not only do I have the same code as what the user was using in production, because I know what version they were on, but I can roll back my local data. I can redeploy basically my local data to that version of the data though. So that way I can replay the data exactly as the user did, reproduce all their actions, and just stop it at the point where the issue occurred. And not only then I can use my IDE to debug the problem, but with production data. And without having to worry about connecting to a production database, because it's just a copy of that. That's really powerful because it means developers don't need to be debugging against production to get production data access. And that is something that I've used before that is really, you don't need it often, but when you do need it, it's kind of something you can't replicate with traditional solutions. Once you find and fix the bug, and maybe you issue a few correction events, how do you then update the system to have this new data? Well, usually in a traditional system, that might mean updating lots of tables in a database with some kind of correction, migration. Maybe the users have to go in and mess with something in the front end. But again, with an event sourcing system, once you fix once you've issued a few correction events to fix the actual event log, then you just delete your databases, delete your derived views, recreate them. It'll rebuild your derived views, and that means they've been recreated as if the bug never happened. So your current system state then is correct, but you still have that event log showing what the bug did occur. So you don't have to worry about, well, what about the fact that, in your traditional system, after you've fixed it, there's no evidence the bug ever happened because you've updated all the bad data with good data. In the event sourcing system, you've fixed it now, and in all your derived views, it's as if the bug never happened, but you've still got the original event log that proves not only what happened, but how you fixed it, when you fixed it. So if you want to say, okay, well, the bug was a problem between this date and this date, well, you know what those dates are because they're on your events. So now you know exactly what data was affected. You don't have to send some blanket email to your users. You may or may not have been affected by this bug. Sorry. These are the users that were on the system in that time. These are the users that were affected. Let's either fix it or issue an email or whatever you want to do. You can make very specific actions because you know the very specific impact of that bug. Another advantage, tracing data as it comes through the system is really, really important when you start moving big data around. Well, with an event source system, everything's an event. So because you're not losing data, you can always trace it back. Obviously, things like correlation IDs are really important. We do that in Vivo. Everything gets tagged with a correlation ID. And in fact, things can join together. Event streams can join together. Event logs can join together. When you're processing them, you might process 3 or 4 event logs and have one output event log. So you might need to be able to know what the source for correlation IDs were. Well, the point is that you need to be able to say, when something happens, what caused that? What was the first move? What was the first thing that caused that? Okay, this SMS got sent out that didn't work, and the very first cause was some user pressing a button on the screen. That's quite obvious, but the very first cause might have been also some automated job kicking off. And the fact you can differentiate between them at this point, at the final point, when you're looking at your logs, you can say not only, okay, this event succeeded, this event failed, what's the difference? Well, this was triggered by an automated job, this was triggered by a user. So you immediately have got a lot more context around these things when you're trying to figure out what actually went wrong. Again, talked about this before, so I won't go over it, but easy to expose data. It's a really key point that not about just having the data, making sure that data is available for new users. And again, one that's an advantage to us in Vivo and an advantage to some people is the functional approach that event sourcing really is. Because the current state is a left fold. It's the aggregation of all previous behaviors. So the current state is just the aggregation. That's what your derived views are. Your derived views are some kind of aggregation or summation or, final view of the state, the previous behaviors, previous events. And I mean, I don't know if we talk about snapshots. Did I lose my one about performance? Did I mention that in the performance one? Sorry. I'm going to skip to that. But one of the things you can do with, so I mentioned it here because I've mentioned it, but one of the things you can do if data storage becomes a problem, I think I've lost a slide, is you can have snapshots. So we've talked about how the ideal situation is to keep all data forever. If either due to financial reasons or data protection reasons or whatever, you can't do that. You need to have a specific time window that you store a number to. A solution to that is to use snapshots. So you basically say, this is what the data will look at that point in time. So looking at a customer's bank balance, rather than storing the whole history of every transaction they ever made, you can either you might archive some of that storage or keep it, but you might stop having to process all that again every time a new container starts or whatever, a new service starts up. You may take a snapshot at a specific point in time and say, okay, on the 1st of August at 10 p.m, their balance was this. So when you start in future, you don't need to start from the start, you start from the snapshot and you process down from there. And a snapshot is a cache, a memorization of your aggregate. A snapshot is just a cache. Another functional technique. And Kafka Streams, which is what we use, even lets you use functional principles and functional programming to define high-level declarative approaches to processing our data. So we'll definitely do a talk at some point on Kafka Streams because that's one of the things we're really keen on. And it lets you define how to operate on a stream of events as a very high level, map this to this, and then it just operates on your whole data, on your whole unbounded, infinite stream of data. So the future of event sourcing, I think a really important thing with technologies like this is, because event sourcing has a learning curve. I'm talking about it at a very high level here. I'll give you guys a chance for questions, but I'm sure There's lots of them. This is something you have to spend a lot of time and get your head around and dig into if you're interested in it. Is it something that's got a future? That's a really important point when you're looking at new technology. Well, I think the fact that it works very well with functional programming, which is something that's gaining a lot of traction. It works very well with cloud computing and distributed architectures because of the scalability. Again, something that's very popular and is obviously, even lately, is still growing. It still seems to be growing, but is already very, very popular. It works excellently with microservices. Again, something that's very, very popular and always seems to be growing from strength to strength. It's an obvious implementation. It's a very popular implementation of event-driven architectures. And CQRS, again, is a very popular concept that even without event sourcing, it's going to become very coupled because they are very closely linked in, I guess, the technical consciousness. And the key point is that distributed logs aren't going anywhere. They've been around for so long that distributed event logs are going to be needed regardless. So event sourcing from that perspective is always going to be something that's good to understand. How do databases share their data across nodes? Things like that. How does Git share data between different people? This is how it's all powered. So a little bit like just in Vivo, how we use some of this stuff. So, functional programming, we use Kotlin. We did historically use C# and object-oriented programming. We now use Kotlin with Arrow, which is a functional library, kind of enhances some of the functional aspects of Kotlin but still letting us be comfortable, I guess, from people who've come from an object-oriented background. From that perspective, I think we found it really, really powerful. We've simplified our code base. It's been really, really useful for us. And one of the reasons we switched to Kotlin, because we all really love C# in fairness, most of us are C# developers in Vivo. One of the reasons we switched to Kotlin was the better Kafka support from the libraries. But in reality, we've just found that Kotlin is a really powerful language. But it just works, when you're using these functional languages, the fact that it works so nicely with Kafka streams is just, which is just really great. And again, we'll talk about Kafka streams, I think, definitely in a future talk, because we find it's one of the best parts of Kafka. But the core concept is that, functional programming and events logs just go hand in hand. Cloud computing, we use Azure. This allows us to scale out when demand is high. And what the event sourcing architecture gives us is a very obvious way of checking how we falling behind on our processing. Because all our events are a stream of events, it's a log. We can see if there are 100 logs and we're at log 50 processing that, and there are 50 more, and they're coming in as fast as we're reading them, we know we need more processing power. So it's an obvious indicator that we need to scale out to handle that. And that gives us the chance it's a very easy metric to gauge how far behind are we falling from the event log. Because these are asynchronous systems by definition, you need to know, how big a problem is it? If it's powering an API, you don't want it to fall too far behind because that could mean the user getting stale data. But if you're powering some, backend service that no user's going to know if it's a minute late, it's sending SMSs, no one's going to really notice if their customer gets an SMS 1 minute later. That's fine. That's fine to fall a little behind. But it gives us the opportunity to make the right decisions then in regards to cost analysis and when to scale. Similarly, microservices, we deploy into Kubernetes microservices. This allows us to scale out even easier. Again, that's a talk for another day. Matt's going to touch on Kubernetes in his talk next, and how Kubernetes and event-driven architectures, event sourcing tie together to make a nice zero downtime deployment possible. But at its core, Kubernetes just allows us to scale out easier and cheaper and faster, which is really important when you could have these big, it's kind of something about how in Vivo work, but we tend to have a lot of our customers still working in bulk processors. They're not, using real-time data feeds. So from that perspective, they're dumping a lot of data at once on us. So it's good for us to be able to scale out in response to that. And microservices obviously help with that. And CQRS, again, we've talked about this. We're using Kafka streams. We use Kafka streams to build state stores. So Kafka streams basically lets you build for free these read-optimized key value stores for our APIs. So when I talked before about the CQRS having 2 different models, you may have thought that sounds great, except you don't want to maintain 2 different models. It's extra work. Kafka streams is technology, and this is why we love it really, that makes that much easier because it basically manages the store for you. It does that through RocksDB basically. So you only need to build your own read models if you want to use something like SQL for very complex relational queries, or you want to use some, graph database for machine learning algorithms, or for, looking up relationships between nodes and things like that. But otherwise, with very little development effort, you can have a simple key value store implemented for basically for free. That's it. Oh, so this is a bit I thought I'd read, but I moved to the end. If we have a lot of events, won't it take a long time to iterate all over them all? Yes, but this is why you have your derived read-optimized views, e.g. a SQL table. And yes, but you can also use snapshots if you need to reprocess an event stream frequently. If you've got an event stream that you're constantly having to reprocess because you're starting new containers, and for whatever reason, those containers can't just pick up where the last container left off, they need to do a completely fresh processing, then in that, for example, it's a machine learning training algorithm or something like that. In that situation, you can use snapshots, so you don't have to pull history of data to store. If we store every event, won't that mean lots of data to store? Yes, again, that's true, but storage is cheap. And if it becomes a big enough problem, you can use snapshots, but very few people have enough events to cause issues. We store our data in Azure. It costs, when you compare the cost of the storage of the data to the actual processing costs of that, it's pennies. The processing is what costs us much more money. I'm not saying there aren't use cases where that's different, where you're not processing the data very much and you're pulling in, terabytes and terabytes or petabytes and petabytes of data. In which case you have to make a decision, a trade-off between how long you keep your full data, maybe you archive it off somewhere. But for us, we just keep the whole data stream, and it's cheap. That's cheaper. That's a much lower cost than the actual processing of that data. What should I store in one event stream? You can put things into one stream that conceptually group together, or you can put things in one stream where you care about the order, because that's the beautiful thing of an event log. It gives you a guaranteed ordering. But in reality, the tools you're using may dictate this. Event store works very differently. For example, Kafka. We use Kafka, we use schema registry, which doesn't enforce, but kind of suggests one schema per topic, and we follow that. There are ways to get schema registry working with multiple schemas, but we don't really do that. Schema registry is something we'll probably talk about again in another talk, but schema registry is a good way of managing evolutions of your schema, which I think is another point. Yeah, how to evolve my schemas. So what if I publish the wrong data into my event stream? So this happens in real world event logs, financial logs, and this is where the correction events I mentioned earlier come in. You issue a correction event. You either you issue a reversal of the first event if the first event was wrong, and then issue the correct event, or you issue the delta correction event. So you figure out what the change, you accidentally debited £100 when you should have debited £50. Well, then you just credit £50. That's the delta between them. And it's still in your event logs. You've still got the proof it happened. You've not changed the history, but you've fixed it. And that's how you do it in a financial log. If you were doing an audit of that, you'd expect to see a correction event if there was a mistake. How do I evolve my event schemas? And this is one of the things that people always ask because it isn't trivial. If you've worked with event-driven architectures and event sourcing specifically, you'll know that if you're keeping the whole history of every event that ever happened and you want to start changing what those events look like, how on earth do you handle that? And this is where tools like schema registry can help you. They'll verify that you've not changed your schema, you've not evolved your schema in such a way that you've broken compatibility with your previous versions. So we introduced schema registry a little bit later down the line from when we were actually starting doing event sourcing. And to be honest, we probably should have done it earlier, because the value it brings is it doesn't guarantee you can't publish a message that your consumers can't consume from, your downstream process can't read, but it is very powerful and it stops you. Again, it needs a talk of its own, but it's a way of monitoring your schemas and how they evolve. Because when you're writing to an event log, all your events, you need a way to manage that. So what you do is the thing that writes those events can check with schema registry and say, is this a valid version? Is this data valid? Does this data fit the schema? And schema registry can then say, and you can set it up to say, only allow changes that are backwards compatible with all versions, which is how we have it in Vivo. Or you can say, it's got to be backwards compatible with the last version. So you can do kind of rolling upgrades and things like that. And that's it. If there's any questions, please feel free. But I'll put these slides in the meetup afterwards, and I recommend looking at some of these. This is where, these are some of the things I've read years ago, or even more recently for bottom one, Mastering Kafka Streams in KSQLDB. That's the book I've found relatively recently that I found really, really insightful around Kafka Streams. Kafka, the Definitive Guide, I massively recommend because they're coming out with a version 2 soon, actually. But that's kind of the book that explains a lot of the stuff I've talked about today, but goes into more detail because obviously it can. And yeah, I recommend Greg Young, who's a big proponent of this. You will see some of the examples I've used have been stolen shamelessly from him because he has a lot to say about this and it's really, really interesting. And the log is written by Jay Krebs, who's kind of the head engineer, or was the head engineer at LinkedIn when they built Kafka. And that is a really good blog post around, again, kind of some of the stuff we've talked about. It's high level, not Kafka specific, but it's talking about you need more depth, the stuff I've really discussed here, and how it works on a fundamental level. And you'll see similar things discussed there, about how they don't do optimizations in Kafka on writes because of how the log allows them to just do append-only writes, which are very, very fast sequential writes. So that's that. I guess first, any questions from anyone either online or in the office? Yeah, of course.
We've got personal experience, the idea of, say, you read only source.
Yeah.
You say you had an issue like,
yeah,
you process your event and it was wrong.
Yeah.
You read source, you're talking about, rebuilding the database.
Yeah.
I'm just curious what sort of personal experience you had of, okay, so I've got the wrong database, I rebuild the right one. You hot swap them.
Yeah, so for anyone on the call, just if they didn't pick that up because the microphone's a little bit sensitive or not sensitive enough. The question was like, we're talking about evolving, rebuilding our data stores when data changes. But if I'm right, the question was, could you like hot swap a database where you build a completely new database, potentially a different technology and things like that? You're thinking?
Could be.
Yeah, and then you allow them to swap them. So that's not something I've done. I've done the rebuilding databases quite a few times, and that can be useful. Often if you're kind of spiking something out or you kind of don't know what your final schema should look like for optimal use case, you can change the production of that final database and just reprocess your events. When you've lots and lots of data, that can be quite slow if you don't have a way of automating it. So that's something I've done. But there's no reason, you couldn't produce that in parallel. And it kind of will touch into the next talk, which Matt's going to do, about zero downtime deployments, where, you could optimize. He's going to talk about, touch on blue-green deployments, where you can have a primary system and a backup system. So that'd be a really nice way of doing it. Have the backup database. It might take you a while. If you've got a lot of data, it might take you hours, even days to populate that database, that read view, depending on what you're doing with it and depending on how long your history is. Now, there are techniques you can do to speed that up. Don't get me wrong, there are optimizations you can do to speed that up if you need to. Our APIs, we deploy multiple times a day, so we can't afford to wait days for them to populate. They spin up in seconds. But to go back to your question, yes, you could 100% spin up a secondary database, be still using the first one, and then when you see it, maybe run some tests against it, some tests against your secondary database to make sure it's valid and that the data schema has given you, let's say, the performance improvement you were hoping for. And if that matches what you expected, then you just swap them. You hot swap them, and now suddenly you've got this new schema. Your users never saw any downtime, never noticed the difference. You've got the advantage of, they're exactly the same data-wise because they're both reading from the same source of truth. So yeah, 100% that would be a really good way of swapping those out. Whereas with a traditional model, you'd struggle. You'd have two replicas, and one's tends to be the read replica, which then how do you switch which is the master and slave, and it can become quite tricky. Any other questions? Any questions online? Okay, cool. Can you guys hear us okay, by the way? I mean, not hear us, but Matt, can you just speak, make sure I can hear everyone okay?
Yeah, we can hear you fine.
Great, well, thanks everyone. I'll hand over to Matt now to do his talk. But cheers.
Thank you, Jamie.
Thank you.
Right.
You want me to stop sharing, Matt?
Yeah, I can hijack it.
Okay, I'll mute the microphone on this end as well, just so we don't get any feedback.
Okay. So, hello everyone. My name is Matt Swarbrick. I am a senior software engineer at Invivo. I joined in January 2020, just before all the lockdowns happened. But yeah, worked about 3 months in the office and then been working from home since then. It's been interesting. It's been the same story for a lot of you guys. Yeah, so kind of following on from what Jamie's been talking about, we're going to look at kind of a bit of a concrete example on how we use an event sourcing at Invivo using Kafka and hosting our services in Kubernetes. So something we've been refactoring the kind of legacy code base into this kind of event-driven architecture model, and so we've been starting to heavily use Kafka more and more. And as we're using it more, we're kind of starting to find, new problems start to crop up. So this is one of the problems that we've had to deal with and work out, which is the zero downtime. You sell an SLA to a client, and you have to have 99.999% uptime, whatever it is, and you need to make sure from a technical point of view you can meet those requirements. So yeah, so we're going to look at how we achieve that in the Kafka Streams-backed APIs hosted in Kubernetes. So hopefully it may be a bit technical in Kafka and Kubernetes side, but I think hopefully I've kept it conceptual enough, so should be good for most levels, I think, but yeah, we'll see. So the problem, let's say we have an API which manages users for our website, and it has a simple get endpoint and a put endpoint. So get is you retrieve a user by an ID, put is you create or update that user. So 2 endpoints. And like Jamie was saying, with the CQRS model, you have a model for get and a model for write. Very simple. Now these users are stored in Kafka on a topic, we're going to call it users updated. And the put action, all that does is produce a record to the users updated topic. And the get action will query one of these key value stores that Jamie was talking about, which is built via the Kafka Streams application. So very basic setup. So with this setup, when you start an API, you need to kind of initialize the store, get that ready, and then start the API. You can start receiving requests from users. So the point being, there's a little bit of time before the API is actually ready to receive requests. And you'll get this with any kind of, if you're using Kafka Streams, so, you're building a topology, doing whatever you're doing, and you could have multiple stores. It could take, normally it might take seconds, but it could take minutes to do something. And you want to make sure that when users hit your API, that it is actually ready to receive those requests. So if we look at this in a bit more detail, so let's say in Kubernetes, we've got a version of our API currently running. This is 1.0.1, and we want to deploy 1.0.2. So our CI pipeline, we have a CI pipeline, and it builds a new Docker image for the new version, and tags it 1.0.2. It then runs a Helm deploy, which essentially informs Kubernetes that we want to, we've got a new version that we want to run. And then what Kubernetes will do is say, cool, all right, I'm going to delete 1.0.1, create a new pod, and start run a new container in it for the new image 1.0.2. And then when the container starts, Kubernetes will kill the old one and send all traffic to the new one. So the problem is, during that deployment, Kubernetes will prematurely send all traffic to 1.0.2, where it may still be setting up its state store or whatever it's doing. It might not be ready to receive requests yet. So the users are going to experience some downtime. Not ideal. A solution. So with Kubernetes, there are many different strategies and deployment strategies you can do. You've got a world of configuration at your fingertips. Very powerful orchestrator. So if you don't use Kubernetes, we do recommend using it. You can basically achieve anything you want to. And like Jamie was saying as well, it handles scaling and auto scaling for you kind of easily as well. So one of the deployment strategy that we've used to solve this problem initially is the rolling upgrade deployment, which basically you have the existing instance of our API running, and you deploy a new one. They run side by side for a bit, and then when the new one is ready, it switches over. So that's how we're going to solve this problem. So you've got 1.0.1 is running, it's receiving all the network traffic. 1.0.2 is Kubernetes has been told to deploy it and get it ready. So it starts it builds its store, starts the API, then Kubernetes goes, cool, you're ready, let's go, let's route all the traffic to the new one, and then it kills the old one. Right? Very simple. Which leads us on to KISS, keep it simple, stupid. It's one of our core principles at Invivo. Generally, as engineers, we like to over-engineer problems. We like to kind of create these amazing solutions for things using all interesting technology and things. And that's great, but often you need to build in a way where, obviously in your team, you need the whole team to understand, and also it needs to be maintainable. If a new person joins the team, they need to be able to pick up this technology and work with it. So generally, a simple solution is often a lot better than a kind of over-engineered solution, even to the point where you may even lose a bit of performance or efficiency because of the future maintainability of your kind of system. And take event sourcing, for example. Jamie's saying, 4,000 years old, but it's still around today and it's used pretty much everywhere. We don't even realize, because it's so simple. That's why it's stood the test of time, because it's so simple. You look at Kafka, you think, flip, that's pretty complicated. Initially, you may look at it and go, I don't really understand this, and you get your head around it. But actually, it's built on very basic principles, very simple principles, and that's how we should build our stuff, is build it upon these kind of simple principles, you build on it. So anyway, back to the point. There's two main things to get this rolling upgrade working in Kubernetes. There's two kind of key bits to set up. You've got the Kafka setup and the Kubernetes setup. So with Kafka, we've got two instances running at the same time. So there's a bit of an overlap. And when you deploy a Kafka Streams application, to have multiple instances running at the same time, they need to be able to consume off one of these, append-only logs, these topics at the same time. So the way you do that is you partition a topic. So what we've got, each of our topics, so our one called user updated, which stores all the user events, the user updated events, it will have two partitions. And this will allow a second instance to join the consumer group, and it will be assigned to partition. The existing API, which was previously assigned to both the partitions, will be shifted onto one, and they both start consuming at that same time. And then the other thing, which is probably a bit more technical on the Kafka front, but basically with Kafka Streams, they do this thing called rebalancing. And what that means is when a new instance joins this consumer group and starts picking up these events, a rebalance occurs, and that's what kind of causes the instances to be assigned to these partitions. And that actually happens from time to time. But the problem is if the Kafka Streams app is in a rebalance state, and a user says, "All right, I want to access this user, please," and it does the get action on the API, it goes to query the key value state store, it's going to throw an exception, and it will return an error. So what we recommend is very simple retry mechanism that will alleviate the issue. Wait 100 milliseconds, try again, maximum retry count 3 times. That works. And because rebalancing is very quick, with a simple retry, the user probably won't even realize there's any degradation. So that's it. That's the Kafka kind of setup done. Really, not much more than that. Obviously, there is a bit more technical side to it, but kind of from a conceptual point, that's kind of enough for now. Might do a follow-up talk, especially if we start looking at blue-green deployments, which we'll kind of touch on a little bit at the end. But this moves on to the Kubernetes side, where we're actually hosting our Streams app. So again, we're running multiple instances in parallel. And so because we've got multiple instances, we don't actually want traffic to hit our new instance until it's ready. We don't want users to actually be hitting that new API. So Kubernetes has these probes, which basically test, you kind of define a test and it will probe that and you'll get a pass or a fail. And so the 3 probes are startup. And what this does is you define this test, and when it passes, it informs Kubernetes that, yep, this container's fully initialized, it's ready to go. And so once that passes, it won't run again. It kind of does it once kind of thing, or it keeps doing it until it passes, and you can define thresholds and things. And then you've got these 2 other probes, liveness and readiness. The liveness runs continuously after a successful startup. And basically what happens here is if this fails, it informs Kubernetes that something's gone really wrong with this container and you need to stop it, you need to kill it, you need to create a new one. So this could be if, you could have like a memory leak, for example, and the container is just unrecoverable. So your liveness test would fail, Kubernetes would kill the app, restart, create a new one, and then you've still got, you've got uptime still essentially on your You know, it hasn't just gone down. The user's suddenly reported, hey, I'm not getting any responses back. You know, it's kind of self-healing in a way. And then obviously you're going to deal with the memory leak issue behind the scene whilst, you know, you're still giving some uptime. And then the readiness probe is really similar to the liveness. It runs continuously after a startup probe, but instead of Kubernetes killing the container and creating a new one, what it does is it kind of puts a fence around it, and it just stops traffic from reaching it. So it kind of sits there, but it doesn't actually cause a restart. So you're probably looking at these and you're thinking, well, you could solve this downtime problem using a combination of these probes or whatever. So what we started off with, and this is kind of that KISS principle again, it's like you have an MVP, a minimum viable product, but in terms of problem solving. So how do we solve this problem in the minimum, you know, in the simplest minimum way that ticks all the boxes? So kind of phase one was, oh, okay, we could have a health endpoint on our API. And when you query that endpoint, returns a 200, you know your API is running, right? Well, that's all it does. It just returns a 200 response. Super simple. You can set that as your startup probe. So when the container kicks off and it's running this startup probe, as soon as it gets that 200 response, Kubernetes is informed, yep, the container's good to go, and it will start routing all the traffic to it. And that will actually solve the problem in this scenario. That will actually fix our downtime issue. It was just with a simple health endpoint and a startup probe. But we've taken it as our MVP for it, we've taken it a bit further with, instead of a health check endpoint, still a health check, but it's actually a smoke test. So obviously, when you're engineering products, best practice is having a test suite, an automated test suite. So when you write a new code, all your tests run. If they all pass, your code's good. If it fails, you know, you've broken something somewhere. And as part of that test suite, you probably want some form of an integration test. You know, whether it reaches a real SQL database or a real Kafka cluster or some other API somewhere or something. You probably want to just make sure that you don't want the user to find out that you've broken some SQL or something. You want to have that slightly automated. So what we've decided is we want to do that in the actual environment that the product's going to run in. So I guess traditionally, if you have an integration test, you probably build some kind of test infrastructure. You know, you'll have a test database that you've got to build up, make sure it matches, you know, what production's like. But maybe you're cutting costs, so you want it's a bit cheaper version. You kind of, with an integration test, you want it to be as identical as possible to what production is. And I guess the best option then is run it in production, right? So instead of the health endpoint that just returns to 200, we have a smoke test endpoint, which in our case of the user API, we'll do a put, create a new user, or update a test user that we, you know, reserve test user, whatever. And then you do a get, do you get the user back? You know, do you get 200 responses from when you do those requests? That's it. Not only have you tested that the API is reachable, you've also tested that it still works with Kafka, it's still functionally working, you know, jobs are good. So that's pretty much it. So on to the demo. So let me end this. Okay. So let me kick this off. I need to run the pipeline to demo this. I'm going to do a real deployment right now. This is our Automate API. And what I've got on the right-hand side is I built a simple tool called a downtime deploy tool. And essentially, when I was working on zero downtime deployment, I wanted to make sure that as it deployed, there was no downtime. You know, to test these probes were good, to test the smoke test was working as expected, to test that when you know, Kafka was rebalancing, that it didn't cause some downtime. So built a simple app that basically hits that smoke test endpoint, and if it gets to 200, it prints OK, and with the timestamp, so you can see it's kind of doing its thing. And to prove this isn't like some kind of fake app where it just prints out dev OK and a timestamp, I go to the actual Automate API in our dev environment. I delete the pod, On the right, this should start kicking off saying, okay, it failed. Hang on. Embarrassing. I knew something would go wrong in the demo. All right, let's try that again. I'm blaming Azure. There you go. So I delete the pod, but in here, you see, it now says possible downtime. It's not running, so obviously you're going to get these 503s returning. So on the left-hand side, you can see, yep, that it's terminating the old one. Obviously, it's creating a new one. So that's the cool thing of Kubernetes. What I've done is I deleted a pod, but Kubernetes knows that it's been told to deploy an Automate API, so immediately it'll create a new pod. If you're unfamiliar with Kubernetes, it's one of the powerful features. It kind of you tell it the state of your application or your services that you want to run, and it will just go and try and meet that state as best as it can. And whether that means scaling up nodes or deploy, whatever it is, whatever you tell it to do, it will do until it hits that state. So right now it's deploying a new version. Now what you see here is it's actually running the container, but you see it's 0 out of 1. This is the startup probe happening right now. So basically the startup probe hasn't passed, so it's not actually available yet. So that should pass fairly shortly. And then in the right-hand side, it will say, dev OK. So it's running here, and then so on the right-hand side, you start seeing that it says dev OK. So this tool is quite useful if you want to build proper zero downtime. It's quite useful to have something like this, a test as you're deploying, so that it will pick up any downtime. Because obviously, if you do have downtime, the user somewhere is going to find it out and and raise some support request or something. Anyway, back to pipeline. The kind of frustrating thing is you've got to wait for a new image to build as well, which takes a couple of minutes, but it won't take too long. Whilst we're waiting for that, are there any questions or anything?
A difficult one.
Oh, it's a difficult one, Matt. Get ready.
My
Flip.
small exploration into Kafka, it got difficult when I wanted to upgrade Kafka. So it was deployed to Kubernetes, and I got all my mounts and disks or AWS ones. And the update was really difficult. So I don't know if you've got any thoughts on upgrading Kafka and.
Do you hear that, Matt?
No,
Okay.
can you repeat that, please? Or Jamie, can you say?
It was basically around upgrading Kafka itself. So you've shown obviously how we upgrade a given service, but what if we want to upgrade the actual instance of Kafka? And to be honest, I can answer that, which is we cheat because Confluent hosts our instance basically for us.
It was a good way of doing it.
Sure. Yeah, exactly. Because of exactly what you're talking about. We looked at hosting our own. We thought about it heavily because there are some limitations with Confluent's cloud version and it's more expensive. But realistically, you'd have to have people just managing that stuff. And same with Kubernetes. We don't host it ourselves. We let Microsoft host it for us, and we just chuck containers into it. Basically, it's because you're right, Winston. That gets difficult. That gets very hard to manage that kind of thing.
Exactly. Yeah. Well, that's it. Like I say, Kubernetes is exactly the same thing. We let Azure kind of manage it for us, and we kind of all we worry about is actually deploying something, which is very useful for us.
Yeah, we still have some learning curves. I mean, I think we might talking about KISS as well. It's worth mentioning that it may sound a bit ironic when we're using some quite complicated technologies to say keep it simple, but there is a bit of a learning curve, and we understand that. But once you've learned these technologies, we do think they make their day-to-day lives simpler. If that makes sense. They help solve some very difficult to solve problems that if you had to solve yourself, you really would struggle with. And that we try to historically, the businesses try and solve them themselves, and it's kind of like there's definitely an argument to be said that some people take on stuff like Kubernetes too easily because it's a cool technology, and similar probably with Kafka. But there's also a point to say that they definitely simplify things down. But that's why we've gone for the hosted solutions rather than our own managed solutions, because it massively cuts down the amount of work. Like if we had to manage Kubernetes ourselves and Kafka ourselves, I do think we wouldn't have gone for them because we're only a small team. We've 6 or 7 developers now. We've gone up to our biggest, we were 10 or 12 developers. We're only a small team. We haven't got the resource to be having 1 or 2 developers just managing that infrastructure stuff. We try and build these cross-functional teams where we all work together.
Yeah.
Any other questions? Rich, any questions?
Not for me, mate.
Josh? Josh did say, Matt, that he's been told not to delete things from Kubernetes. Can you explain that?
Yeah, you should let your pipeline drive the state of your applications in Kubernetes. We'd be manually deleting stuff. I'm getting very cross with Josh around that. Josh and Peter. Yeah, just you probably noticed as well that when I killed that pod, obviously I was demonstrating downtime, but right now we have 0 downtime deployment. But if a pod crashes and has to restart, there's quite a bit of downtime. So, like I say, you kind of keep evolving. You have a solution, and then you keep evolving upon that with a much better solution once you kind of work out where you need to be. So, obviously, we need higher availability now. And part of that is
sorry, Matt, we missed the last bit.
Just saying that we need when I deleted the pod, you saw there was quite a lot of downtime. So right now, if a pod crashes and it has to restart, there's quite a bit of downtime. So obviously, yes, we've got 0 downtime deployment, but whilst it's running, if something happens and it has to restart, there's quite a bit of downtime. So obviously we're not quite there with the availability we need to be, but we've got a good foundation to build upon right now where we can start building these really advanced techniques such as blue-green deployments and other kind of deployment strategies where you can have, entire clusters in standby where you can kind of switch over once they've been, when you deploy a new version, you get it all completely ready. But yeah, so right now in Kubernetes, you can see, if I zoom in a little bit, I don't know how well you can see, but we've got 2 running side by side. They're both running. The one hasn't passed its startup probe test yet, and the existing one that's running. So the existing one's been up 7 minutes, and the other one 23 seconds. So if I refresh, you still see, both side by side, still running. On the right-hand side, you've got the status of the API, but still 0 downtime. And then eventually, it takes about a minute for the startup probe to pass. So that's initializing the state store and hitting the smoke test endpoint, running the smoke test and getting 200 responses. And I think there's 10 seconds. The startup probe has like a 10-second interval. So it kind of, it will pass any time now, essentially. But hopefully, you won't see any downtime. So far, so good. Yeah, so I think the next thing we'll probably look at is, so right now we have a replica set of 1, so only ever has 1 running. But I think we're going to have, a couple with 1 in standby, essentially. So right now it's terminating the old one, and the new one's running. So you've updated the API, 0 downtime.
It works the other way as well, Matt, right? So if you deploy out an API and the build fails running the API because you've made some changes that actually broke the build, it's obviously clever enough then to say, oh, this one's broke, we're going to keep the first one running and we're not going to have any downtime on the opposite way, I guess.
Exactly, yeah. That's the smoke test. You're functionally testing that. So if it doesn't work, it won't do the switch over. Exactly right.
Also roll back the new one, right? And delete the new instance of the application because it recognizes the new instance is failing. So it will delete the new instance and keep the old one running.
Yep. Yeah, it's the atomic setting in Helm. If there's any failure for whatever reason, it completely rolls back to your state.
And again, that was one, because we're using Kubernetes, which might have its own massive learning curve, but once you've got it, that's one line of just saying it's an atomic operation to do a deployment. As Matt said, it's just one line.
Yep. Cool. If there's any other questions, that's it. Job's a good one.
Is that any questions? No? Brilliant. Thanks, Matt. Turn his camera on to get his applause.
Hello.
Take a bow.
It's still raining, so I'm practically in Manchester.
Yeah, it's stopped here, I think, actually, for once. Yeah. Right, well, thanks everyone. Hopefully everyone enjoyed the first, the inaugural in vivo tech event-driven architecture meetup. Obviously, wanting to do these about, like I said, every 4 weeks, beginning of the month, every month. We're going to try and do some cross promotion with the Confluent team, who run their own in Manchester as well, for Kafka specific. So we're hoping this can be more of a generic one, and for different technologies. But like I said, Confluent are going to come in and speak, and we're potentially going to go to their meetups and speak. And yeah, it'd be good to get some cross promotion there. But generally, yeah, hopefully we'll start getting some more numbers as well as meetups start picking up again, and we start seeing more things in face to face. If anyone's interested, we can close online. Thank you. For everyone who's in the office, if you're interested, we can go for a beer. I don't know if anyone's bothered. There's a pub around the corner. Obviously, there's only a few of us here, but I don't mind having a chat and a beer with anyone who's interested. Otherwise, yeah, thanks for coming, everyone, and hopefully see you at the next one. Cheers.
Cheers, everyone. Thank you.
Thank you.
Thank you, guys. Bye-bye.
Bye.
Cheers. Thanks.
Bye.
Bye.